Hi, happy almost weekend. It's Friday morning. I am going to do a video on the normal random variable, identical to the one it's the same worksheet I use for the normal random variable when I did integration, but this time I want to show you how to use the normal table to compute these probabilities. So exactly the same problems. In fact, I copied here the answers that we got using the when we used the integration, just so you can compare. But in the future, I don't care which method you use. If you want to go, if you want to integrate or if you want to use the table, either is fine. Sometimes the answers will differ slightly. The reason I even think, you should be considering the table first, sometimes it is very much easier. But second, I've taught like a study course for the FE exam, and at least in the review problems, they have shown in the statistics section that you should be able to use a normal table to compute probabilities. So just in case this ever comes up in the future, or if you plan on taking that exam, this would be nice to learn it right now. It's definitely not that difficult. So going back to this first problem, the length of some steel sheets manufactured by a company were approximately normal with a mean of 75, standard deviation 1, and we're supposed to find the probability that the sheet selected has a length between 74.5 and 75.8. So I'm going to let x be the length of a randomly selected sheet. Okay, and I'm trying to find the probability. This is what we did the other day, 74.5 less than x less than 75.8. Okay, so what we did the other day is we said, hey, x is a normal random variable with a mean of 75 and a standard deviation of 1. So all we did was we put these values into the probability density function for a normal random variable. And then we integrated between 74.5 and 75.8, and we got a probability. So, I mean, you can always go to that way. That is actually what is happening. The table is just trying to simplify it, especially for people that have never done integration. I imagine a lot of people take statistics. They would not even understand what we're talking about integrating a function, perhaps if they've just had algebra. So another way to do this is to convert this to a standard normal random variable. So the conversion, well, first of all, let me talk about a standard normal. Every stat probability book reserves Z for a very, very special random variable called the standard normal random variable. And it's the nicest possible normal. And nicest possible means it has a very nice mean, a mean of 0, which centers it at 0 on a, the bell is at 0 on the real number line, right? The bell is there. And then sigma we're going to set as 1, which makes very nice in the denominator of that probability density function. So it gives you at least a nicer looking normal density function, but this is called, just so you know, for a standard normal. So every time I go and I write a Z, that's what I'm talking about. And in the future, when you see a Z, we try not to use other random variables to be Z, because pretty much everyone understands that Z represents a standard normal. So, every normal problem, you can't have a table for every mu and sigma. So it was decided we would just have one table for normal 0, 1, and then when you have a problem, convert it over to this scale. Okay, so let me show you. I brought my table up. The table is in the back of the book, but I also have an Angel, the standard normal table for you to download. This is, yeah, like the one from the book, and I think it's a nice one. Right up here, I think I can draw on this. Here is the, right here, I'll circle it. This is the density function for standard normal. As you can see, minus x minus mu, mu is 0, so we get a little bit nicer up there in the numerator. Sigma is 1, so we just have 2 times 1 squared, and there's a sigma out front over here, right, but it's just a 1. So anyway, this is, at least looks a little bit nicer. And what this table does is it finds the area under the curve of a normal 0, 1 up to some point z naught. Okay, so for example, let's say I want to find the area under the curve up till about 1. We'll put a line here at 1. I want to find all of this area. So I go to my table, and over here is 1. I can hardly see this thing, so let's go to a pen. A red pen would help. So let's go over here. Here you see 1. And up here are the what do you want to say, hundredths decimal place. So 1.00 is 8.8413. That's how much area is under that curve up to 1. If I want to know how much area is under the curve up to 1.05, you would come down here and you would go across here. And this is the area under the curve up until 1.05. And notice, I mean, the more you go left, the more you go right, the more area you pick up. So you notice, like, as you get to, let's say, 2.07, you've picked up 98% of the area under the normal curve. So really, yeah, it's just telling you how much area is under the normal curve up to a certain point where you're using a standard normal. So I want to go back over here, and so we'll go to this table when we want to find probabilities then. The only problem now, back on our Maple worksheet, is to be able to convert to a standard normal. So to convert to a standard normal, what we're going to do is we take the x value, we subtract off the mean of the random variable, and we divide that whole thing by the standard deviation. And now you'll see that I convert to z because I have a standard normal once I've done that conversion. So 75.8 minus 75 divided by standard deviation, which is equivalent to finding the probability. Let's see, 74.5, isn't that negative 0.5 is less than z is less than 75.8, should be 0.8. Right, so I'm trying to find the area under the z curve between 0.8, between negative 0.5 and 0.8. So let's go back to this curve. Well, first, how much area is under the curve up till, what was that, 0.8? So let's see, here's 0.8, 0.80 is 7881. So 0.7881 is the area to the left of 0.08. Okay, and now I'm going to subtract off the little bit of area, well, not a little bit, but a little amount of area to the left of negative 0.5. So let's go back to our curve. A negative 0.5 is down here, and that leaves 0.3085. 3085, and the area under the curve then is 4796, and let's see, we had gotten 4796, so not too bad, right? So that is one way to do it. So I hope, you know, that I did 2 and 1 here. I had to take to the left of this and subtract off to the left of that, but I hope that makes sense. Then I have a lot of other examples in the notes if that didn't quite work for you, but let's try another one. Sorry, my windows are open. Suppose scores on a dexterity test, mean of 12, standard deviation 3. So x equals dexterity scores, they're normal with a mean of 12 and a sigma of 3. Okay, great. If 8 read randomly people, we don't really care about that at the moment. So what's the probability that none will make a score less than 14? What's the probability of a score less than 14? And when we used integration, we got 7475. So what's the probability? We are trying to find score less than 14. So this is the probability of z less than, because when I do, right, when I standardize, I get a normal 0, 1. So I take 14 minus 12 divided by 3, which is, I think I have on my parentheses, z less than 2/3, which is approximately p, probability of z less than 0.67. So on a normal table, let's just go to 0.67. So let's get back over here. Here's 0.6. I'm just going to travel across so I don't lose it. 0.67, 7486. So 0.7486. And so, yeah, we don't perfectly match up, but, you know, that's I mean, sometimes you will. I mean, again, there's a lot of area under that curve right at the bell part. So sometimes when you're right at the bell, you're not going to be quite as accurate. There's, you know, you're picking up a lot of area even if you move a little bit there because you have that bell shape there. I'm not going to figure out the rest of the question. I really just wanted to see the probability that we used in that problem. Here's the one out right. I kept going back and forth on the other day. Let's see if I can't do it better this time. Suppose that lifetimes of light bulbs produced by a certain company are normal. So x equals bulb lifetimes. They're normal with a mean of 1,000 and a sigma of 100. Okay, it's covering when it collects at 95% of its light bulbs last at least 900 hours. So we found the 95% cutoff when we integrated 835.51. So if I just want to know what value leaves 5% in that left tail of a normal 0, 1 curve, what I'm going to do is go back to this curve here, and I'm going backwards. So now I'm trying to find the area under the curve and what value leaves 5% to the left and 95 to the right. So let's go to that. Can we make it bigger? Oh, that would be help. Okay, so I'm looking for 5% inside this table, and you can see I'm not doing a very good job at here. We're getting close, 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 close. So it's in here, right? And again, about rounding, you can go 1.64, 1.645. I mean, it's not the case that it's always just the average because it's not a linear function, but a lot of people, like you can see 5%. I'm going to go with 1.645. So the 95% cutoff on Z plot is negative 1.645. So if we want to find then, if I go 1.645 standard deviations to the left is where that cutoff is. So this is what I'm going to do. 1,000's the mean, and then I'm going to subtract off that many standard deviations, and my cutoff's 835.5. So yeah, 95% of their bulbs are not at least 900 hours. I mean, 95% of their bulbs are starting at 835.5 hours. So I don't know. Does the chart make sense how I did that one? I mean, I think the thing to look at in this chart is inside are the areas under the curve, and then on the outside are we call them z-scores or z-values that leave that much area under a curve. So, for example, how much area is under the curve up until negative 1.3, what is that? Where are we going? 1.34, about 9%. And no, I mean, this makes sense. When we get to 0, 50% of the area is under the curve, right? 50% to the left, 50% to the right. So I hope this helps. This was a long one. And I think I'll do an exponential a little bit later.